This is the beauty of VAE, right? That is the beauty of VAE, that you can represent it in a latent space.
Right now, the model doesn't have any understanding of what data we're actually putting into it, right? It has no notion of how to reconstruct sequences or what the correlations are amongst the sequence data, right? So training is going to be the moment where the model starts to learn, oh, here are the correlations amongst the different parts of the sequence and whatnot. And then it'll start to organize the data in the latent space. That way, when you actually pull from the latent space, you get meaningful values back out.
Okay, good. So I think we just reconvene from where we left off, Vedant, right? So last time you were showing us how to create this protein sequences and how to represent the protein sequences in a latent space. And then from there, now we are trying to training the model and generate sample data out of it. So really excited, waiting for that. I think this will be my 22nd episode of Generative AI in Enterprise. And also, just FYI, this video will be recorded and shared in YouTube. So no IPs, no confidential information we are sharing. The other thing is, like, if you're concerned about speaking or talking or being recorded, so please keep that in mind. Feel free not to, but also let's participate and make this session engaging. So I'll stop, and Vedant, over to you. No more chat.
Sounds good. So last we left off, it's exactly as you said. We had just started coding up, or not just started, but we had started coding up our model. And I had walked us through the process of creating a data set. So this was converting this CSV file, which was nothing more than, a set of sequences and a bunch of metadata associated with each sequence, into tensors. And I showed us how to do that. So if we quickly remind ourselves tabbing through that data. Sorry, let me just go ahead and yank the code back up so that we have it, so that we can get through it. We now have an object that is indexable, and that when I make a call to assert one index value, I get an X and Y value out, and that X and Y value corresponds to some representation of what is otherwise sequenced data, into some numerical representation that a machine learning model can actually digest. I then started walking us through building the different parts of the deep neural network. So I have the encoder module right here. I have the decoder module right here. And then I started building out the variational autoencoder. And where I left us with was just having built the forward pass of these models. That is, like, data goes in and something comes out. But what I didn't yet talk about is writing down the loss function and building out and computing losses and using those loss functions to train, right? To actually do minimization, to do training. So what I'm going to do for us right now is actually go ahead and go through the process of getting that piece of information out. So I'm going to make a few quick changes from what I had done initially. The first of which is, initially I had defined these as log standard deviation. I actually want to define them as log variance. It'll be a little bit more convenient for us down the road. So this is not like a huge substantive change or anything like this, but it is a small quantitative change that will make a difference for us going down the line. Now we're at calculating the loss. So the first part of the loss is something called binary cross entropy. So binary cross entropy, especially for categorical data and things like this, estimates basically is a calculation for when you're doing classification or categorization, how far off you are from the true label of the data set. So computing a loss for how far off the true label of the data point you are. And Torch actually has a built-in BCE loss function that I'm going to point out to us right here. I tend to prefer coding it up myself every single time, just because when things are math, unless there's like a very, very unless there's a very strong reason, like the compiled version is so much faster than whatever I can type out in Python, I would rather write it myself, because then I can see the math in action. So we have as arguments to our reconstruction loss function, we have an x and an x hat, right? X hat is our prediction, and x is the true value. So the loss, which is per item, is going to be simply the true value, right? Going back to this function here, it's true times log of false, true times log of predicted, plus 1 minus true times 1 minus log of predicted. Basically saying, pay attention to when we're right, and also pay attention when we're right about, when we're wrong. Pay attention to both parts of the equation. So try to make sure that you're right as often as possible. So then you get something like torch.log x hat plus 1 minus x times torch.log 1 minus x hat. Now, worth noting, the log function is always unstable when you start taking logs of very small numbers. In particular, the logarithm of 0 is not defined. So I often include this very small float, which just makes sure I don't accidentally take the logarithm of an undefined number and cause my model to nan out. Cool.
Now, just all this loss function is already there. There are functions.
There are implementations of this, but for many of the default type of classical ones, there are functions. This one in particular, there exists one, but the next one I'm going to write out, there actually doesn't exist a pre-built one, so we're going to have to write it ourselves as well. So I think it's just useful to say like, okay, loss functions I can write myself in general.
Okay.
I'm going to make sure I take the mean of the loss across all of my examples, and that's going to be what I return as my loss. Terrific. So this is the reconstruction loss. Now, if you'll recall, when we talked about variational autoencoders, one of the things we had also insisted on was that they make sure that the mapping to the latent space match to a certain distribution. They need to be matching to a multivariate Gaussian distribution with unit variance. So this part of the loss function is sometimes called elbow loss or something like this. And what it's basically doing is it's trying to place a constraint on z mu in z log var, or log var, I guess. So I need to make sure this return is the log var. I guess I forgot to name the variable correctly. Z log var. We're gonna go ahead and try and ask these to be as 0 and 1 as much, obeying that multivariate Gaussian with the unit covariance as much as possible. So this particular function, I often always refer to what's in the actual original paper to do this calculation. And you can see the equation is written out for us right here. There's no inbuilt torch equation for this, but it is just an arithmetic expression, right? So that's pretty easy to write down. Well, it's going to be 1. So loss will equal 1 plus so z log var, right? Z log variance. This term is the log of the variance term, so I don't have to do anything. Minus z mu squared, right? That's going to get us this term right here.
Mm-hmm.
And this is just the variance itself. So, oops, sorry. That's just going to be torch.x z log var.
Okay.
Right? And I'm going to make sure that I take the mean of all this, because this is going to give me many numbers across many dimensions for each example in the batch. And then I'll return that as my loss. So now I have the two components of my loss, right? I have this and that. So let's go ahead. So these are now attributes of my class. Let's go ahead and take a peek and see how they work. X is not defined. Oh, okay. I know why. For batch in data set. I think what I've forgotten to do here is load my data generator. So you remember my data set gives me one example in that tensor representation. My data generator, which is coming from this torch utils data loader object, is what gives me mini batches that I can use for training. So I forgot to reinstantiate that from this session to last session.
Okay.
Oops. Great. So no problem. Let's take a look. So we have, again, our z mus, our z log vars. Terrific. And now what we can do in z, so one thing we can quickly do is we can just plot these. We can plot these and see what they look like in the default case. Scatter z Oh, good. So I often forget that you can't directly plot tensors in matplotlib. You have to detach them, and then you get some 32 points that are scattered about the latent space. Great. Now we were calculating loss functions. One thing we should do for loss functions is quickly check to see what they actually look like. So if I do example VAE.recon loss, x comma y, y comma x, right? We put the true value as the first argument. I guess we should name this y for clarity's sake. Good. And I bugged. Okay, good. I see why I bugged. This is just because I passed it a dictionary instead of the key to the dictionary, and I get some loss function. Now this loss function is 0 for some reason, so we should inspect why that's the case. The reason it's 0, I see, is because I passed it the true value, or rather I passed it just what the input was, which is incorrect. Right, I need to pass it through the model. We need to take our input through the forward pass of the model and get what the model thinks the decoded versions of this should be. And now we get this. Now we get this. Can only concatenate tuple, not float. Awesome. Now I'm getting to see where I messed up. Oh, good. Okay. So as we remember, example VAE spits out several arguments, more than just one argument, right? It spits out the z mu, z log var, z x hat. I'm only interested in the x hat component.
Oh, okay.
So when I calculate this recon loss, it's on x hat. And so when we go ahead and calculate it, we get some output out, some loss function. There it is. Our loss function is negative 0.192. So that actually does let me know that I made a bug. A reconstruction loss should always be strictly positive. What I forgot to do is I forgot to put an overall negative sign out there. I owed an overall negative sign. So now I fixed that.
So let me try to understand. Yeah. So we took a protein sequence. We what was that technique that we used to mod something, right?
One-hot encoding.
One-hot encoding, right? So we did one-hot encoding to kind of like encode the protein sequence. And then after that, we are trying to create a latent space of that protein sequence, and that's what you're showing over here.
That's what this is. Yeah. So now
that's what this is, right?
Embedded it in some latent space, right?
Embedded in some latent space. So basically, all these pointers over here are the positions of that one-hot encoding, right?
So yeah, each point corresponds to a protein sequence embedded in some latent space.
And then how did we generate all these different protein sequences? We generated them out of.
So right now, these are all sort of natural. These are all sort of what's in the.
This is coming from the CSV file.
Yeah. So now if I wanted to,
got it. Okay.
So now if I wanted to generate one, I could pick a point in this space and decode back.
Decode. Okay.
Yeah.
So I took a CSV file. I took a protein sequence out of it. I know how to do the encoding. Then I ran it through the model. This whole CSV spreadsheet that was like maybe 2,000 records or 5,000 or million records.
Yeah.
And condensed or compressed into this latent space. And this is the visualization of it. This is the beauty of VAE. Right? That is the beauty of VAE, that you can represent it in a latent space.
Yep.
Fine. Now the next beauty of VAE is like if I train the model in a way, I mean, that's what I'm trying to connect that out. So now we want to take a pointer from this space and generate back. But where is the model training coming into picture?
So we haven't actually trained the model yet, but we've just calculated the loss.
Why do I need to train the model one more time?
So right now, the model doesn't have any understanding of what data we're actually putting into it, right? It has no notion of how to reconstruct sequences or what the correlations are amongst the sequence data, right? So training is going to be the moment where the model starts to learn, oh, here are the correlations amongst the different parts of the sequence and whatnot. And then it'll start to organize the data in the latent space. That way, when you actually pull from the latent space, you get meaningful values back out. Right now, you're not getting, right now, it's just sort of a random initialization condition that we're looking at.
So basically, when you train a model, okay, we'll see how you're going to train the model. But when you train the model, you're going to somehow adjust the weights and balances of the
Mhm.
model to create a meaning out of the data set. That is the interesting part. Okay, let's see how you do it.
So the way I would go about doing that is sort of straightforward now, right? So we're going to say for epoch in, range epochs, and we'll say epochs is the number of times we'll iterate through the data set. We'll iterate through the data set, let's say 1,000 times. Maybe for this conversation, we'll just do 100 or something like this. I don't know how much I have to train for. I will, for batch in data generator, I'm going to go ahead and I'm going to go ahead and do the forward pass of the model. This is the forward pass of the model. So where I actually do inference based on the current state of the model, right? One thing I forgot to do is just create an optimizer. So torch dot, sorry, give me 1 second. Torch dot, yeah, this is what I'm looking for. Great. So in Torch, we have this submodule called Optim, which has all the optimizers of the module. So this is sort of like the actual methodology by which you estimate the gradients and update you estimate the gradients and then you update the weights of the model according to those gradients. So Atom is a very common gradient updater. Common way of updating the weights, optimizing the weights. It's called like adaptive something of the means or something like this. It just basically makes sure you're making reasonable size steps at all times. So for this, we need the params of the model. So that's example VAE dot parameters or something like this. We need the learning rate, which this is something you would tune in general. I'm going to take it to 1e minus 3. And there are many other things that you might kind of want to set yourself or something like this. One of which, I think the most common that people care about is like something like weight decay, which basically says like over time, if the weight is over time, maybe you want to say, I want to have some weight decay because if I'm not updating a weight constantly or my updates to my weights is not sufficiently large, I want to actually start sending them to 0. That's a way of regularizing a model or something like this. And the other is gradient clamping. If gradients start to become too large, you can cause yourself to have like overflow errors in your weights. You can cause them to go to NaN or something like this, and that'll negatively impact your model training. This happens when gradients explode. It's the so-called exploding gradients problem. Cool. So I have my optimizer, I have my forward pass. Now I'm going to go ahead and quickly calculate my losses. No, sorry, accept. Good. And then my KL, my elbow loss is equal to example VA dot elbow loss. And we remember that what we passed to that as an argument was the Z mu and Z log var, which I've gotten for us right there. Z mu, Z log. I guess I didn't test that, so maybe we should just quickly check and see if it's working. Oh, I forgot to give it a self. Good catch. Terrific. Oh, this is cool. So we get a number out exactly as we're expecting. Awesome. So now our total loss is going to be recon loss plus elbow loss. And now from this, we can do something called total loss dot back. This is basically going to be calculating the that's going to be calculating the actual gradient step for us. Sorry, that'll be actually calculating the gradient against the weights of the model for us. Then we need to actually take a step. So that's going to be achieved by doing optim.step. This updates all of the model parameters by one gradient step. Notably, at the beginning of each instantiation, like the gradients sort of build up, and you don't want to be relying on gradients from many steps ago as a part of your updates. You should set them all to 0 at every step. So in the beginning of every loop of this model, we should do this zero grad. We should zero out the gradients. And so this is a training loop. This is in and of itself enough to train a model. One thing that'll be sort of convenient for us is if we can see the loss go down as a function of time. So I'll just have it print recon loss item. This will print the recon losses for us to let us know if we're going in the right direction. And we can go ahead and run it. And check that out. So you actually can kind of Let's see, is this number decreasing? This model will definitely overfit eventually, but I'm not sure what it's doing. It'll actually be easier if we just keep things in a tracker. Good, 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 good. And now let's go ahead and let this thing run. And we'll see, is the recon loss actually going down or not? I mean, one kind of core challenge is often you're training a model and your loss doesn't go down. So you panic and say, why is my loss not going down? And here we can see that my loss is actually going up, which is quite alarming and tells me that I've done something wrong.
Our primary goal is to minimize the loss, right?
Primary goal is to minimize the loss. So one needs to take, so this kind of error is not, unfortunately, usually the result that the error is between the keyboard and the chair. And so it becomes my burden to now understand what has gone wrong. So if I look at x hat, if I look at just one example of one of my inferences and compare that to the right value, so it seems like it's totally optimized to the wrong thing. So the question I now have to ask myself is, am I pointing it in the wrong direction? Have I pointed the gradients in the wrong direction so it's just consistently walking in the wrong direction? That's totally possible, actually, right? Yeah, it just seems like it's optimizing in the wrong direction. So maybe the sign, maybe I still have a sign error that I didn't quite appreciate that I need to fix now. Let's go ahead.
How would you know that? How did you know that?
Well, the way I knew that is because, okay, so good. The way to know that, the way I know that the gradients are in the wrong direction, rather.
Isn't because the loss was increasing?
Well, partly because the loss was increasing, but also because it was probably, the model was probably better when I didn't train it. The fact that the model was better before I started training it means it must have been walking in the wrong direction for some time. And so the way to see that it was better, before I started training it is you can see that I reinitialized the model here. Cool. You can see that like this is actually closer to the right probability than this is, right? This is putting all of the probability weight on totally the wrong thing. Right? This was from our failed training run. It's putting all the probability weight on the wrong thing. Right? It should be over here, right? Which is what? 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. All the weight should be over here, but it's ending up over here for some reason. And then if I look at like a brand new random initialization, all of the weight 0, 1, 2, 3, 4, 5. Yeah, there's actually some probability weight in the right spot. So it's actually completely walked in the wrong direction, which means I've probably made a sign error or something like this. It's not the end of the world. So let's go ahead and see what happens if I fix that sign error, see if things get any better. And now the loss is going down. We'll later have to confirm to see, okay, has it actually learned anything, or has it just made a mistake? Is it still making a mistake? It seems to have totally gotten stuck. So I suspect I've made some bug that's going to take me some time to figure out. Oh, shoot, I just did that. Oh, dumb. Oh, I have to do that again.
Is this a day in a life of a...
It's not terribly dissimilar to how I spend my day.
That's what I'm saying, right?
Yeah.
Day in a life of yours.
Yeah, so I mean, there are many more talented data scientists than I am who will not make this many bugs who are working.
That's okay.
I mean, like working through.
Not actually a data scientist, but I have been a programmer at some point of time.
Yeah, and so I hope that some of these struggles are, at least somewhat familiar.
Yeah, absolutely relatable.
Yeah,
in a different domain, but absolutely relatable.
Yeah, so somehow this is still, bugging and pointing in the wrong direction. I can sit here and debug this for some time, and we could actually spend time doing that. And I probably will end up going back and asking the question of how I messed up. But very fortunately, this is not the first time I've done something like this. This is not the first time I've coded up a VAE in my spare time. And somewhere in my GitHub, there exists an implementation of a VAE. Let's see if I can find it.
The last,
This is a specific flavor of a VAE that maybe is not super pretty or something like this. But let's see. If I built the class out somewhere, you can see a lot of the features are there. But somehow this is not what I wanted. There should be another one that actually has like the actual correct thing. Yeah, VQVA versus VA. Good. So part of this is what I want, but I don't want exclusively this. Yeah, here we go. This is actually what a VA should look like. I've done all the work here to make it work. We could pull this up if we like and dig through it. It actually does look like put the minus sign in the wrong place. How did I do that? So somehow it looks like I had argued over here minus half times 1 plus this times this, that. Okay, over here, I didn't give it the minus 0.5, but there's 1 plus.
But that should come from the formula that you were trying to use.
Yeah, so the question is just,
There's not something that there is a half over there. Is that correct?
Yeah, there's a half over there. So I missed the half. I also put that as, this is plus. I just typoed I typoed this. That should have been a minus instead of a plus.
But eventually what you're doing is you're taking this equation that has been part of a research paper, trying to implement that and see and give it some data and see later.
Correct. Yeah. So
long back, I think 25 years back, like when I was in college, I was lucky enough to be part of a research project in Statistical Institute of India, ISI, Kolkata. And we some pattern matching or pattern recognition project using Visual Basic. So when you showed me that paper, it kind of like recalled, I was able to recall that, okay, we were in through that. Yeah, I was handed over this little paper, and it was so cryptic. It took us so much time to even decipher like what's going on over there. But eventually we kind of like did that similar thing, but using Visual Basic, long back.
Yeah, no. I mean, this is like the dirty secret of doing this kind of work, right? It's like some of these papers, they're not like, it's not always obvious and intuitive exactly how to read them and and understand what's going on.
God. Yeah, we and a couple of my friends spend almost like 2-3 days just looking at the paper. Like, what the heck is that? We are not from a core mathematical background and all. Of course, like I had my maths honors, which I almost forgot.
Yeah.
This was like after our MCAs and also we had to do some project, and then this professor gave us a paper. Little bit.
Yeah.
So difficult to decipher.
Yeah. No, but the devil's always in the details, right? And you see, like I fixed that 1 minus sign, and all of a sudden the loss function is going down.
Correct.
And
even for us also, right? When I recall now, in the first 2 days, so that professor gave us that paper and he was gone. And then 2 days we were just looking at the paper, did not know. But then gradually when we started looking at it, okay, let's go one by one, word by word. Gradually we were able to understand. So not rocket science, we were able to understand. We were able to, it took us some time to kind of like get into that zone. Yeah. So yeah, devil is in the details. So now you're looking good, is it?
I think it's still slight. I mean, the reconstruction loss went down, but it didn't actually. I don't know if if I just messed up and just reinitialized the model by mistake. So I should just do this every single time so I don't make this kind of mistake consistently. So if I print the total recon loss, the number is some number. Is it going to go down slowly? Yeah, so the learning rate might be too small right now. So right now the number is going down, but it's going down quite slowly, as you can see. It's making very small, very small amount of progress at every step. Okay, learning rate's too small probably. It's taking too long to learn for my taste. Let me make it faster and so by the way I made it faster, I increased the learning rate. This comes with its own risk. Maybe now things will, it may make bigger jumps in loss space, and that might cause it to make more mistakes or something like this. Let's see if we can actually get it to train all the way. I'm a little bugged out by the fact that it's training. So I'm going to keep looking for bugs while this is running in the background.
Just so, Vedant, just so I understand this, right? So you essentially you created an encoder and a decoder. You took a data set, which you essentially encoded first, right? So you took a whole lot of parameters and basically brought it down to a smaller subset, right? Which is the encoding piece. And then you have a decoder.
Is it no. Is it correct? Or like my thought was he took the protein sequence, which was in that Excel spreadsheet, and not only the protein sequence, there were like a bunch of other things, but I think he took the protein sequence, like hundreds and thousands of them. And he took one of them, he did this one hot encoding to encode that into a digital format. Now, my question was, okay, why didn't you took 1, 2, 3, 4? And then he mentioned about like the bias. That if I took 1, 2, 3, 4, 10 or 26, then the model might think bias. So they went with one hot encoding. So that A became that encoded big binary thing. The B became another big binary. So now he has the data set of that protein sequence.
Right.
Now,
So this one hot encoding is just a step to get it from into the character space into some numeric representation. That is not the encoder of the VAE.
Not the order of the VAE.
Not the encoder of the VAE.
No, not the encoder of the VAE. Correct.
Yeah.
So that is the data set, which is the one hot encoded representation of the protein.
Mm-hmm.
It's a huge binary kind of like a set. Now I'm taking this data set and passing it through the VAE's encoder so that it can be compressed down into a latent space, which is that visual representation.
Yeah, so that big tensor gets passed through an encoder and gets compressed into a two-dimensional space. Precisely.
Yeah. So two-dimensional space.
Yeah.
And the reason why we are doing this, and I was also doing some reading like after our last call, difficult topic. But the reason why we are doing this is so that as humans, we have something to refer to, like understand. Is that the reason, or is there any other reason also?
Well, that's not the whole.
Not the whole. I think no. It's a. Let me.
But that's like a very nice.
There is one portion of that. But I think one of the reason is like once you compress it to a latent space, one is like I think that was one of the questions that I was asking. That why are we even compressing, right? So the reason why we compress is basically, why are we compressing, by the way? Hey, before that, Vivek, did you get your answer, or did I took you in a wrong direction?
No, that's fine. I was trying to just, I think where I was trying to go was, essentially to summarize, right, the entire life cycle in the steps, right? And where I was going was essentially with the learning, right? What is being done is now you take another sequence, you pass it through the same, you use the same thing, use same encoded sequence to decode, and then see how closely did it decode compared to what gives them.
So that's the part of the training cycle, right? That's calculated.
That is part of
it, because now it's able to decode, right? On this model, it's able to decode the closest it can possibly be. Then you basically, and when you have your losses minimized, that is where you now say that the model is trained. Now you can pass it a novel sequence, and it will be able to generate an output, which is what you're really wanting to do.
So what do you mean by the novel sequence? I thought it's the opposite, right? Now we are picking a point from the latent space to generate novel sequence.
That's right. Yeah. So once you have a trained latent space, you could pick a point in that latent space and decode from that. Right. The idea is basically now you've learned a function, an invertible function that takes you from sequence to latent space, and you can invert that function to go from latent space to sequence. Now you can pick a new point in that latent space that's never been observed from your real data and generate a new example. That's
And
basically
that
what.
generation part is called generating novel data.
Yeah, it would be generating a novel. That would be the generation in generative AI.
Generation.
Yeah.
Hey, Betty. Thanks for joining.
So right now we're just debugging code. Sadly, we're seeing if things work or not. And for whatever reason, right now my I've stumbled across a bug that it might take some time. Or it might need to.
I need
more
to create a
training.
visual representation of this one, like a flow chart, which is very simple to understand. Because the moment I'm out of this, maybe everything will go away.
Yeah.
You
So
lose the whole concept. I think I'm in a much better shape than 4 weeks back, but I definitely want to capture this in a visual representation somewhere.
yeah. So I think in earlier slide decks I've kind of showed like.
No, I have to do it myself so that it gets into my sluggish
Yeah.
brain.
Why? This must be some very, very simple bug that I've stumbled across. And
So once you're done debugging this one, like maybe we'll discuss one more time that why do I even have to compress or create that latent space? Compress and create the latent space. What are the benefits?
that's right. Okay. So where is it coming decoupled? Where is it coming decoupled?
Hey Betty, just to say hi, thanks for joining. Can you hear us okay?
So it's coming decoupled somewhere. I'm gonna cheat here and see if I can't force it to work a little bit better. So the other kind of trick now is, okay, so now the model's not fitting for whatever reason. And so the question is like, can I overfit the model? Because if I can't overfit the model, then I know the bug I've made is truly quite nefarious. So I'm going to go ahead and try and overfit the model and see if when I overfit the model, it works. Because that'll help me identify like where it might have broken down. And now you can see here I've imposed a very simple constraint where I ignore the stochasticity in the training piece, and you can actually see it's actually coming down. Let's give it a few epochs to kind of try and settle down the loss function. When it hits maybe 25 or 24, we'll inspect and see if it's starting to come to the right thing. If it hits 25 or 24, who knows where it slows down. It's already pretty good compared to what we were seeing earlier. Yeah. So earlier we were seeing a lot, like comparing absolute loss terms is not always the most useful thing in the world, but like because we're doing the same model many times, like we can kind of compare the terms. Initially we were seeing losses like 34, 35. Right now we're seeing losses of like 27 or so. Which is like kind of a good sign that things are kind of trending in the right direction. That this sort of simplification actually did come of some use. So I'll quickly stop us here.
This is recorded, right? All of that is recorded.
Yeah, these are all recorded at here the YouTube channel.
And you will send us the link because maybe it makes more sense for me to look at this from the beginning instead of in the middle.
No problem at all. So I'll share the link for the YouTube channel, so where I'm going to post this video. And this is, by the way, did you join earlier? Or this is the first time you're joining?
Well, the same person was I heard the last time when he was talking about the sequence.
Okay. You were.
Yes, yes.
Oh, I remember. Like, yeah, you found a
And
bug.
I liked it very much actually, and I wanted to do it on my own. But unfortunately, my laptop got broken, and so I am on my cell phone for the whole week. So
No
I cannot.
Yeah, I
Yes.
remember you found a bug last time.
Yeah.
Yes.
You called I think my typo on enumerate very specifically. I remember that.
Yes, that's
Exactly.
true.
Yeah.
That's true.
Correct.
That's true.
I mean,
Which was
good.
appreciated.
Yeah, I mean, like the last video is already uploaded in YouTube. I have sent you the link. Curious Circuits. This one I'll also upload.
Okay. Okay. Okay, so maybe I will leave here because so I can start from the beginning. But I do enjoy very much that those sessions. So thank you so much.
Yep, absolutely. Thank you.
Nice.
Okay,
Nice
bye-bye.
to get that feedback.
Thank you.
All right. Cool. So while we were chatting, been just checking to see like with this like overfitting trick are things working out a little bit better? And one of the things you're seeing is like where the maximum inferred probability is actually matching where things should be. So things are actually trending in the right direction now. So we've made progress, which is huzzah. So realistically, what does this mean? The big change that I made was instead of doing this reparameterization trick, I skipped the reparameterization and just took this part of it, just the z mu part of it. So I've taken out the stochasticity part of the variational autoencoder. And so what this is telling me is actually something is going wrong in the reparameterization part of the model. And so now I could sit there and debug and just think like, okay, so why is it that changing it to z suddenly causes the problem? And so the way I might do that is, okay, so what are the initial z mu's going to be? Okay, like they're a bunch of numbers. Surprisingly, they're actually all, One thing that's surprising me is I would have expected this to be closer to 0 on average, and this to be closer to this to also be I expected both of these numbers to be closer to 0 on average, but right now they actually are systematically away from 0, which is kind of strange to me right now. And that maybe that's just in my head. No. Yeah, this is not systematically near 0. Why is that true? That shouldn't be right. Oh, what happened? Is this because of because I made the layers too small, so it's like actually having a hard time learning? That actually is not implausible. That actually looks a little bit better. Hang on. Yeah, okay, cool. So now I know what I did wrong. So initially, I had one of the layers going and piping down to like a hidden layer of size 5 or something like this. That's like actually a very small hidden layer. People usually don't do hidden layers that are so small unless they're trying to very explicitly go to a very compressed representation. So I jacked it up to size 100. And this got me, like, I think is actually going to help me quite a bit because I'll actually make it bigger. I'll make it go to 200. I think this is going to help me quite a bit because this is going to give my model more parameters to fit with. And that'll increase basically how much gradation the model can actually have access to, right? The fewer the number of hidden layers, the less expressivity of the model. So it's not so good to be super skinny, especially if you're a deep learning model at the very least. So now maybe when I train, things will be a little bit better. Let's go ahead and give it a shot. So far, is it going to give me the same issues or is it going to give me okay? The way I expect it to. Okay, let's stop it here. This is no good. So right, if I take a look, the elbow loss is nearly 0, which is not a great sign. That loss should be finite. And the recon loss is relatively high. That was maybe just lucky. Yeah, I don't think it's doing a very good job. Okay, cool. So let's take a peek back at what my old thing was and see what it's see how I did it there and see if I can figure out what went wrong in my code. Torch.mean, torch.sum. But this should just impact scaling, right? So if I go from the beginning, but this is because, what are z-mus here? Z-mus have been made excessively small, and z-log vars have been made nearly 0, which means that, right now the model is entirely focused on minimizing the elbow loss term and is totally ignoring the reconstruction loss. I realize I'm kind of like glossing over a lot of the arguments and things like this, but this is sort of like as you spend a lot of time doing this, you start asking yourself the question, why do certain things happen? Remember, our loss term comes in 2 components, right? This is the thing I'm calling the elbow loss, which is the adherence to that 0-1 multivariate Gaussian, and the reconstruction loss, which is given by this term. I think I'm not really reading this equation very carefully, but those are the 2 primary components, right? So when one of these pieces goes to 0 very easily, there's one of these things is satisfied very easily. It sometimes can come at the expense of explaining the other part of it. If it comes at the expense of explaining the other part of it, you're not doing a good job of navigating the trade-off between these 2 terms. And you need to make sure that it's not always good to totally minimize one, because sometimes you end up coming to a suboptimal solution where you could get an overall total lower loss by lowering the other one a little bit more, but you get stuck because you've lowered one of them too much and now you can't move anymore. So one thing I'm going to take a peek about is asking the question, like, how big does this loss get and why does it shrink so much? Okay, so that's kind of starts at not too big a place. Yeah, that's fine. I'm pretty sure I applied nonlinearities. Pretty sure I did that. I didn't apply dropout here, which is slightly different, but that's not a huge deal. Right. But yeah, sorry, this may take me some amount of time to actually totally debug, but the core of it is kind of done now.
That's okay. I wish I can help you with the debugging.
No, I should be capable.
But Katie was good actually. Last time she found at least one bug.
Yeah, she spotted it nice and quick, which is nice.
So basically, over here, the summary is we have the latent space created. Now taking a set of training data and trying to train the model, you went ahead and added, initially you were training, pardon my ignorance over here with some terminologies, but I saw like you added, initially you had 5 layers, you increased that to 100. So basically now you are adding more hidden layers to it.
Well, not more hidden layers, but hidden units. So not the number of layers, not the depth of the number, but the width of each layer. I increased the width of each layer.
Okay, so you are increasing the width of the layer. Okay, and you also made a bunch of adjustments while you were trying to do the training of the data. Ultimate goal is to reduce the loss function, but you are struggling with the reducing the loss function. Is that?
Yep.
Okay, that's fair enough. With a more fewer other adjustments, you will be eventually able to reduce the loss function. Then you will be able to train the model in the way you want it to.
Yep, absolutely.
Once you are able to train the model, let's assume that you have already trained the model. Let's assume, right? You have already trained the model. What would be the next step? I know it will give you some bad data out. But
so right now, this will give me garbage. Yeah.
Okay. Let it get garbage. I want to understand how do you now generate data out of that latent space?
So as you as I've explained, we have now something, example the decoder. We have a method, right, called this decoder method, which is this linear layer out. And so I can say, hey, I'd actually really like to generate a point from maybe the coordinate.
That is my next question. Why would you choose, let's say 1, 0.5 or 0.5, 1?
Good. So
something over here. So I choose this point over here. My question is, I have a set of protein sequences. I put it into a latent space. How do I decide that I need a point from this particular area?
Yeah. So I think the thing to kind of recall is that one of the reasons why it's useful to have these really finite dimensional latent spaces, these really small dimensional latent spaces, is because you can sit down and maybe interpret why certain sets of proteins go to certain parts of the latent space. So what I mean to say is maybe you observe that all of the proteins of a certain type are clustering to some part of latent space.
Okay.
If you remember,
let's talk about the clustering. So can I, just looking at this one, can I think this is a cluster?
I think it's hard to see with this. It's hard to see with this few examples. I think it might be more useful to go back to an older slide deck of mine to see it. But like
I remember the slide.
Yeah.
So where you had like all this green, yellow, blue.
yeah,
Like
precisely.
got it. So with more data. So
Yeah.
basically, you're saying with more data, you will have that cluster created, like the deep colored area, right? That
Yeah.
we were trying to show in the. So let's assume that I have created this. These are some of the cluster. I'm just assuming.
Sure.
So okay, one more question. Why are there only few points, and why are there not that deep more number of data? Is it because our training data is not enough at this point?
Oh, well, it's because this particular example is generated on just 32 points right now.
I see. Okay.
So like
When you
we
say
absolutely
32 point, like, is that the list of the spreadsheet?
no. So there's many more. I've only selected 32 from it right now for this particular example. We could sit down and generate them all. I can do that very quickly if we like. But right now I'm only showing 32 of those points. So that's why it's a little like
No,
opposite.
I did not understand. What do you mean by points? Like, what is that 32 points?
So there's some 7,000 sequences in here, right? Like that's 7,000 sequences. At each step,
right? It's the total number of rows that you have. 7,000.
Yeah. So
you took only 32 out of that?
Right now, this particular example is showing me just 32 of that list. So I can go back and we can generate all of them right now.
Why 32? Why not 33, 31? Maybe I'm
this is sort of a random number that I just selected. The reason to do less than the whole thing, huh?
Okay, got it.
The reason to do less than a whole thing is because during training, you end up having to do calculations on it, and it's not just a static number. Then, like you have many, like you have to iterate through the batches as a part of your training, right? And calculating the gradient against too large a batch size costs too much memory for your GPU or CPU.
Okay.
So you break it into smaller pieces and then calculate gradients against small parts of the overall data set at a time. This is the notion of stochastic gradient descent. There are other benefits to doing stochastic gradient descent, like, you approach the Kramer-Rao bound on the actual value of the parameters, things like this. You get like very nice, you get some more stability of your model, or you get some generalization by doing stochastic gradient descent effectively. But the core reason to do it is because you cannot take 1 million examples or 1 billion examples and calculate the gradient on all of them simultaneously.
I mean, you can if you have the money to spend on the GPUs, right? Parallel process.
Yeah, I'm not sure that even then you need to start distributing it across many GPUs, because I'm not sure NVIDIA or your favorite chip maker makes a GPU large enough for one single calculation or something like this. Right? You need to start doing distributed training.
Yeah, distributed, like parallel distributed processing. Yeah.
You can do these kinds of things for sure.
Yeah, I was going through one of the training on fine tuning. So before fine tuning, like LoRa, and then there were a couple of other. So they were showing like how many, how they can do parallel and distributed like training process, and that's where all the NVIDIA stocks are going up, right?
Yeah.
Okay. So right now it's only 32 point, but eventually you want to train that model with those 7,000 line items that you have and create this latent space.
Yeah, and you can populate this latent space precisely.
But you do not want to use all of your 7,000, right? I mean, you want to use a 80. There is a 80-20 rule, right?
Yeah, you can do train tests.
Like
you can do train test
train
splits
test,
for sure.
right? Okay.
Yeah, you can do a train test split for sure.
Okay, so maybe like 6,000 you use to train the model. So now you have a much more concrete latent space representation. Coming back to the point where maybe visually now you'll be able to see those clusters, which is not clearly right now defined.
Right.
Maybe you're trying to do that. Okay.
Yeah.
And then I'll be able to understand that, some of the proteins sequences are forming this cluster, whereas the other protein sequences are forming this cluster.
Correct.
What do we infer from that, Vedant?
Well, what you infer is that when you want to generate, if you want to generate, you can pick a point from there to generate back a sequence of that type. You also might say, maybe
Huh? why would I try to generate from, let's say, this space, right? So this is space 1, space 2, and space 3. What am I looking for actually?
So one thing that may be true is you may know something about the properties of the protein that you're dealing with, and space 1, space 2, space 3 may correspond to proteins of different properties. And if you are interested in generating a protein that has a certain type of property, you might go to one of those spaces to generate a protein that has the type of property, right? You also may be in a limit where you've never done this. You've never done a measurement of any kind or anything like this, or haven't measured most of your data set. And you may be spontaneously discovering that for whatever reason, these proteins have different properties and are clustering together for some reason. And that can kind of give you an unsupervised way of understanding like that these groups are somehow different and you should treat these groups differently. So that's sort of the value there.
So tomorrow, if I have so one is like I can generate from this latent space. So this is the generation part.
Mm-hmm.
I can get a novel sample. The other one is tomorrow, if I have a new protein sample coming in, right? So someone give me this protein sample. Can I map it to that same latent space and see like where does it belong?
Ideally, yes. Yeah.
Right.
Yeah. Why is... Oh, I lost my mouse. Hang on. There we go.
Very interesting. So we are talking about protein. I'm just trying to think like what are the other applications of this one? I mean, definitely there are so many applications.
Yeah. So here you go. Now you can see the whole density of points. This is an untrained model, obviously, right? Like, let me just make it a little bit better.
The moment you start training, it will start, creating that.
Yeah, it'll start to make trade-offs between clustering points and trying to adhere to that Gaussian 0-1 distribution. So yeah, here we go. Like now I've created some transparency. You can see that the bulk of the points right now in the untrained model is like kind of centered around this value.
Got it.
And of course, this is like the randomly sampled one. So if we look at the actual z-mus, the mean embedding for every point, it should also ideally, yeah, kind of a little tight, actually. Very tight compared to what I'd expect.
But then is the idea like when you start training, it will start creating those clusters?
Yeah, it should start moving them away from one another. It should trying to separate the sequences out and things like this to try and get try and make it easy to reconstruct and easy to generate. And you should start to see clusters emerge up to some, effectively, yeah.
Which visually like our human brains can understand.
Start to process, correct.
So going back to like compression and the latent space,
Mhm.
One of the reason why we compressed and created the latent space is so that I as a human being can understand and then generate sequences out of that space. So can correlate and then generate. What are the other reasons?
So another really strong reason might be that you think that your underlying data is only dependent on just a few variables, right? So we talked a long time ago about like, maybe we're talking about the stock market or something like this, all 500, all the tickers of all the various 500 stocks on the SPX or something like this that comprise the SPX. And we might think, like there's 500 numbers out there that are evolving in time and they all seem kind of, whatever. And maybe there's many variables that correspond to explaining each one of those 500 numbers or something like this. But maybe you actually believe that there's really only 3 numbers that determine the direction of stocks on any given day. And that's the Fed funds rate, the overall, the Fed funds rate, the consumer spending levels, and inflation or something like that. Maybe those 3 numbers are really the only 3 numbers that determine all of the SPX's direction on a given day, right? So now you're saying, oh, this high dimensional data set, which is all 500 prices of all of the stocks in the S&P 500 or whatever, are actually just controlled by 3 different variables.
Yeah,
so that might be a very strong reason to compress.
I remember the example that you gave, right? So for example, I think you were talking about Tesla as an example at that point, 2 weeks back. Okay, maybe because of Tesla doing something, all the EV market is getting impacted, right? Tesla did something and the whole EV market kind of like went up.
Sure.
Or, because of ETFs of Bitcoin, the whole cryptocurrency market like went up. So that is
these
one
things
variable.
move together because they depend on some underlying thing that controls
underlying, right?
structure.
Correct. So that is only one example. There can be more than one factor.
Yeah.
So that's what we are trying to observe as well. So will it be able to observe that? Are we able to observe that based on that clustering that it's created? As a human being?
Good. Now you're getting into the realm of like where things become very hard. Doing this kind of interpretation is, I think maybe one day it'll become robust enough that you can actually say sharply that like this cluster corresponds to this, or machine learning is interpretable enough to let you know why things go this way.
Beautiful.
Right?
Beautiful. Beautiful. Yeah, beautiful. Today, I think OpenAI released one blog post. It's very interesting. And which says that we don't understand how the model works. And they're trying to create something. Have you seen that? I lost it.
Interpretable AI has been like sort of a field for almost 10, 15 years now. People
Got it.
trying to understand these kinds of things. So I'm not apprised of this most recent like paper from OpenAI, but I'm sure like Anthropic invests a lot of time in doing this kind of thing as well. A lot of the big people do, you know.
That makes perfect sense.
Yeah.
So I can take a data set and I'm just now comparing it with a GPT, right? They're taking a millions and millions of data from internet. They're compressing the data through this transformer model. I'm just trying to do an inference, I mean like a similarity thing. So transformer model, they're training the model. They're tuning the model with all those hyperparameters, different layers, maybe weights, model weights, etc. And weights and balances, that's what they call it. Hyperparameter, weights and balances, and layers. And now we have a trained model. Is it similar to the latent space that you're creating over here in VAE? Is it like completely different?
For a transformer, I mean, the dimensionality is going to be much, much higher.
Okay.
So it'll behave quite differently, but
But transformer doesn't create a latent space like this, right? I think that is a very big difference.
it's a not created in the same way at all, and the interpretation is slightly different. Like you could call it a latent space, but it won't be exactly understood the same way.
Okay. Yeah.
Yeah.
Okay. So now, but the funda is like pretty much same, right? I take set of data, I compress it, I train a model with, I compress it using the model, and then I take the rest of the data set, I train the model, I tune the weight and balance, I try to reduce the loss function. Now I have a model which is trained, which is like GPT or which is like whatever you're doing with VAE right now. So I have a model which is trained according to my need based on all these like weights and balances that you are figuring out. Now I have a trained model. Now I should be able to generate novel examples out of it. So for example, that's what we are doing every day. When we use ChatGPT, then I'm now using a trained model to generate novel things out. I ask a question, it starts predicting answers, right? Or start predicting the next set of answers or something.
Right.
And then, and I'm just trying to compare it with our daily life, right? Then our biggest thing in this industry is like, if I use GPT, how do I evaluate the answer is correct? And that's what we were also talking about, like, how do I even infer what is the meaning of this data set and which point I'm interested in? So that is the biggest, piece of the puzzle, because we really don't know how this whole neural network is working internally.
Right.
We're still trying to figure out, like, and I was going through a podcast by Lex Friedman this week, and they were talking about AI dangers. Some person, I forgot the name. So they were trying to talk about AI dangers, and I think it's the same thing, right? There is no clear-cut way to test what is there inside the model. It's like the only way we can test it is by like taking a few examples and try to match it with our expected answers. But we do not know what are the other variations over there. And people are still trying to figure out. So, so interesting, complex concept. Really different.
Yeah. I think you've hit the nail on the head. This is like it's not a trivial thing by any means, right? Like there's quite a bit of like, quite a bit of work that goes into trying to understand like what the models learn and like how successful people are with determining what the models learn is still yet to be, I think, is still an open question, right? Like how close can people actually get with this kind of thing? It's not clear yet.
Okay.
Mhm.
Good.
Yeah.
Good. Thank you. We are almost, we are already out of time. Okay. I didn't
Yeah.
realize also while talking.
Yeah. So I'll try and correct my errors and then send over like a GitHub link or something like that to you. See if I can figure out where I went wrong and then maybe mention it. But this will now be like an obsession for the next little bit. So
Yeah.
Mm.
Sure.
right.
But it seems like people are interested. Like Betty was interested. I know like Aaron was very interested, but I do not know why he did not join. But whoever is
cool.
interested might be benefited out of that.
Right.
So,
Absolutely.
of course,
Sure.
this is not a Bollywood music show where we are expecting hundreds of people to join.
Of course.
Good.
Yeah.
Very good. Vedant,
Yeah.
thanks for your time.
Yeah, absolutely. Sorry, I couldn't quite get a model running like on the spot.
That's okay.
Yeah, this is not too dissimilar from what I spend my day.
That's okay. That's okay. I mean, it's also good to see the code running, so that way it kind of like gets sinks in.
Yeah,
Right? The more we discuss, more we understand this space.
absolutely.
Cool. Okay.
Right.
So
Okay.
maybe like we'll carve out some interesting topic in the future. I'll talk with you if you also have
Sure.
some other ideas that we can brainstorm or learn together.
Yeah, absolutely.
Not learn together. You are the teacher, we are the student. It's like one direction, no bi-direction.
Well, yeah,
It's good to know.
absolutely.
Okay, sounds good. Thank you, Vedant. Take
Yeah.
care.
Talk
Bye-bye.
later. Bye.